Resistance to lateral torsional buckling, Part 7. In order to prevent the possibility of a beam failure due to lateral torsional buckling, the designer needs to ensure that the buckling resistance, MB, RD exceeds the design moment, MED, as highlighted in equation 6.54 in clause 6.3.4.1. However, the beam with sufficient restraint to the compression flange are not susceptible to lateral torsional buckling. The design buckling resistance should be taken as given equation 6.55 in clause 6.3.2.1.3, and is a function of 1. The elastic critical moment, MCR, and 2. The buckling factor, IDRSS double dagger LT, whereby the elastic section modulus, WY, is dependent on the classification of the cross-section. Two methods of calculating reduction factor are provided in EC3 as follows. 1. The so-called general case, mentioned in clause 6.3.2.2, is applicable to all members of constant cross-section. 2. The approach detailed in clause 6.3.2.3 is applicable to rolled sections only. Okay, let's look at the first approach in determining the buckling reduction factor. The first approach can be referred to clause 6.3.2.2. Clause 6.3.2.2 is applicable to all members of constant cross-section. According to the general case, reduction factor is given by equation 6.56, as highlighted in the red box. Meanwhile, the elastic critical moment, MCR, is calculated as shown next. EC3 provides no detailed information on how to calculate the design elastic critical moment of beams, but rather leaves it to the designer to use something appropriate. No reason for this omission is provided in the code. On that basis, therefore, it is recommended the formula for the elastic critical moment, MCR, is taken from the pre-standard INV 1993 Part 11, 1992, as shown in the red box. Bear in mind, the equation in the red box is derived based on several assumptions, which has been highlighted in the green box. Recommended values for imperfection factors for lateral torsional buckling, A ± sign lieutenant, are given in table 6.3. Meanwhile, for cross-section using equation 6.56, it is recommended in EC3 for designer to use table 6.4 and follows by buckling curve. Whichever the buckling curves is used, it must depend on the type and size of section as indicated in table 6.4, and followed by referring to the buckling curve given in figure 6.4, which is shown next. In the case of calculating the reduction factor for lateral torsional buckling, the non-dimensional slenderness is calculated based on the equation given in clause 6.3.2.2.1, which defined as shown here. It is worthwhile to highlight whichever case is stated in 4, shown in the red box, hence the effects of lateral torsional buckling may be ignored and only cross-section checks apply. An alternative method of calculating the reduction factor for lateral torsional buckling for rolled sections only is described in clause 6.3.2.3. Here reduction factor is given by equation 6.57. The value of the imperfection factor, used in equation 6.57, is again taken from table 6.3 shown earlier, but the appropriate buckling curve for the cross-section is determined from table 6.5. In order to take account of the bending moment curve between points of lateral restraint, the reduction factor may be modified as given in equation 6.58, in which Kc is determined based on table 6.6. Given in table 6.6 are the correction factors for various bending moment curves between the 2 points of restraint. Okay, now allocate about 5 to 10 minutes to answer this simple exercise. Next, I would like you to do this exercise. Assume that the beam is only laterally and torsionally restrained at the supports and that the beam sits on 100 mm bearings at each end. No self-weight of beam. Now, check the suitability of the beam to carry the applied load. Suggested allocation time is 30 minutes to 45 minutes. The following slides provide the step-by-step procedure. You are required to provide a solution for each steps given. Step 2. Determination of design shear forces, VD, and bending moments, MED, at critical points. Step 3. Classification of section. Step 4. Resistance of cross-section to bending and shear, ALS. Step 5. Verification on the need to check for resistance to lateral torsional buckling, ALS. Step 6. Verification on the resistance of cross-section to lateral torsional buckling, ALS. And the last step is Step 7, Deflection Check, SLS. We will discuss the solution during the face-to-face session in Google Meet. To summarize. Here are the overall design procedure for simply supported beam of rolled I or H cross-section. To enhance your understanding, it is recommended to all students to go through other types of load cases given in example 9.6, page 402, in the design of structural elements, concrete, steelwork, masonry and timber designs to British Standard and Euro Codes, 3rd edition. Or, you may find the extracted version of example 9.6, which has been uploaded in ECS571 Google Classroom. Okay, thank you. The next lecture is Chapter 2. In Chapter 2, we will learn on how to design plate girder.